Hey, welcome back to Family Physics. In this video, we are going to look at more circular motion, gravitational fields, and objects in orbit. So here we have an interesting case in which we have two objects, two masses of two stars of mass m. They will orbit a common center. As shown in a diagram, the radius of the orbit is r. So yeah, I'm going to use big R. I know the diagram says small r, but I'm just going to use big R. Okay, so that orbit is just r. The mass of the star is equivalent to 1.5 solar masses, so 1.5 times the mass of our sun, and that the initial separation of the stars is 2 times 10 to the power of 9 meters. So this separation here, which is 2r, is equal to 2.0 times 10 to the power of 9 meters, in which the orbital radius is just going to be 1 times 10 to the power of 9 meters. Okay, something to be careful of later. So in this video, I'm going to do all example 3, which is parts A, B, C, D, and E. Oof, pretty long. So let's quickly get to it. State the magnitude of the force on each star in terms of n, which is the big mass of each star. We know that they are orbiting each other due to their gravitational force of attraction, which is going to be the equal and opposite direction on one another. So that is going to be equals to big G, big M, times big M again for the other mass. And since it's times the other one, I'm just going to make that squared. Okay, divided by the separation, which is 2r. 2r is a separation, and don't forget the separation is squared. So according to Newton's universal law of gravitation, that is what it looks like. Okay, r being the separation between the two objects. Since the two masses are the same, that's going to be m squared, and the distance of separation is 2r squared. We simplify this, and it's going to give us big G, big M squared. We're going to put in the, distribute the exponent in, so that's going to be r squared, but 2 squared is going to be 4. Okay, so there we go. That is the magnitude. Okay, next up we want to deduce the period of revolution of each star. So this is going to come from the circular motion aspect of this question, and in which we know that the speed of an object, or actually, you know what? Let's just use the one in your data booklet. Your data booklet says the centripetal acceleration is 4 pi squared. And r is for the orbital radius divided by period squared. Okay, so that we will use for these two stars in orbit. So that's going to be the force due to attraction. That's going to be equivalent to the net force acting on each of these masses, and the net force is going to give us the So the gravitational force will provide the centripetal force needed, or the F net needed, to keep them moving in circular motion. And we know circular motion is mass times centripetal acceleration. So using the Fg above, we get big G, big M squared divided by 4r squared. MAC. M is going to be one of the star's masses, so I'm going to use big M, and then AC is over here, which is 4 pi squared r, nothing there, divided by period squared. Here is where a few things could cancel out, so one of the masses can cancel out there, but all of these down here would need to get multiplied to the other side. So let's multiply for r squared, which gets rid of this. And this is going to give us G, M, General Motors, is equal to 4 pi squared r over t squared, in brackets 4r squared, So I have r squared and r. That's going to give me r to the power 3. 4 times 4 is going to give me 16. So this is going to give me big G, big M equals to 16 pi squared r1 times r to the power 2 is going to give me r cubed over period squared. And since we want to solve for period, let's move period to the top. And let's move General Motors to the bottom. Okay, General Motors here will go to the bottom. And this is going to give us... running out of space. So I'll write it down here. T squared is equal to, the other side is 16 pi squared r cubed over General Motors. There we go. And it looks pretty matching to what we need to find. So there we are. Yay, done. Okay, and C is to evaluate the period numerically. So we know that the period, we need to take the square root of the other side. So that's 16 pi squared r cubed over General Motors. So just to double check all of our values, first of all, we have the mass, which is 1.5 times the solar mass. So 1.5 times the mass of the sun. That's going to be your M value. Our R value is going to be this guy. This is only half of the separation, remember? So we have to use 1 times 10 to the power of 9. And I think that's it. So let's put everything in. Don't forget to take the cube, or to cube the R. That's oftentimes forgotten. I'm putting all this into our calculator. Okay, and I get, let's do blue here. I get 28092 seconds, which is roughly about 2.8 times 10 to the power of 4 seconds. And if I divide this by 3,600, how many seconds in an hour, I get 7.8 hours. Okay, so there you go. Here are the periods. Phew, okay. We're not done yet. We still have to show that the total energy is given by that and the two-star system. Okay, so we still have some work to do. Okay, we're almost there, guys. Total energy of the two stars is given by the following. Okay, so we want to show that. We know that a total energy of two stars is the sum of its gravitational potential energy plus the sum of its kinetic energies. We have two stars, so there's going to be two kinetic energies. But the potential energy, essentially what that is, remember the potential energy is the amount of energy it takes to take any sort of objects, put it in some space from infinity. So I only need to calculate the gravitational potential energy once, because that's just the potential energy between two objects. I take a mass over here, I take another mass over here, and bam, I put them together. How much work does that take? Is equivalent to the potential energy between the two. Sounds like Pico. Sorry. Okay, so let's go and find the potential energy. We know that potential energy is, okay, let's use blue maybe. Potential energy is dependent on, well, it's first of all, it's negative, but it's the constant times the masses, essentially, divided by the separation of the two. The separation is going to be 2r, okay, because that's how far apart they are. So that's its gravitational potential energy, which means that's the amount of work I need to do, well, the positive work I need to do to take two masses. Actually, no, it's a negative, sorry. You have the negative work that I need to take two masses from infinity, put them in some space in which they are 2r distance away. Kinetic energy, however, is going to be a little bit different. We'll use green for this matter. And kinetic energy is going to depend on the orbit that it's in. So we know kinetic energy is equal to 1/2 mv v squared, in which m is the mass, and v is the speed of which this satellite is in orbit. So we did that earlier, actually. So I'm going to take this guy from a previous scenario, a previous question, in which I know that the gravitational force due to attraction is going to be responsible for keeping these stars in orbit, which will be its mass, or actually its big mass, times the centripetal acceleration, which is also equal to v squared over r, in which v is the speed, r is the orbital radius. So if we substitute things in, I am going to get big G, big M squared. Actually, we found that out earlier. That's just this guy here. So that's all over 4r squared, and MAC is just m, and then v squared over r. One of the r's go away because they're on the bottom. Guess what? I just need the kinetic energy. If I have mv squared already, if I multiply both sides of my equation by 1/2, this other side is going to look like my kinetic energy. Okay, because this is kinetic energy. We know this is kinetic energy. That means this side must also be kinetic energy as well. So the kinetic energy of one star in orbit, remember it's one star, is 1/2 General Motors, with which m is squared, divided by 4r. Actually, just 4r. Hey, just 4r. And I have to multiply this by 2 for 2 satellites, or 2 stars. Okay, so that's going to cancel out this guy over here, which means when I want to get my total energy, this is going to be equal to my EP plus EK, negative big G, big M squared over 2R. And I am going to add, since that cancels out, I get big G, big M squared over 4R. If I add these two, you'll find that I get my answer. But let's break it down one more time. So if I did this, this is essentially, let's keep that the same. If I add this over 4r, I'm just going to say this is exactly the same as 1/2 General Motors squared over 2r, in which the 2 on the bottom multiply are going to give me 4. So this is essentially saying -1 plus 1/2. We know -1 plus 1/2 is equal to -1/2. So -1/2 is going to be big G, big M squared over 2r, and I multiply them both together. This is going to be negative big G, big M squared over 4r. Yay, we did it. There you go. Okay? Okay, wow, I bet this video is already very long. Sorry, guys. So last question. So the 2-star system loses energy as a result of emitting gravitational radiation. Deduce that the stars will move closer to one another. So we have to look at the total energy here. So here, for the total energy, assuming that these 2 stars will not lose any mass due to energy conversions, then we will have to look at something else. So if it loses energy, this is going to go down. Okay, so if total energy goes down, keep in mind that this other side has a negative sign. So for energy to go down, then the other side will have to become more negative. So keep in mind of that. So why does the stars have to move closer together? Closer together means R has to be smaller. So if R is smaller, okay, if R decreases, then you're thinking, well, but that makes this whole thing bigger, right? Yes, it makes this whole thing bigger, but because it's negative, then a bigger negative number is going to be less total energy, okay? So if R decreases, then you're going to get a larger negative number. Therefore, energy total would be going down. In fact, if I have to say this properly in a question, So in order for the total energy for okay, so total energy goes down, assuming the masses don't change, that means the radius has to become larger in order for this whole number to become more negative. Okay, so when you explain this question out, when you word it, then you have to explain it so that you're going from total energy to why the R has to be lower. So don't work backwards. Always try to work forwards. Okay, so an example, I took it out. An example of that would be, something along the lines of this. In order for the total energy to decrease, assuming the star's mass don't change significantly, the orbital radius must decrease for the total energy to become more negative. Okay, so that's kind of how I would do it. Okay, I typed it, so harder to put this, write that in a small amount of space. So there you go. This is the whole question. So long question. Thank you for bearing with me. Good luck on your own practices. Thank you for watching. Fan Mama Physics signing out.